Assalamu alaikum. Welcome to lecture number 31 of Software Requirements Engineering CSE305 and in today's lecture we will continue with our topic on methods for requirement engineering. And in our previous lecture we started by establishing that what is the importance of picking a method for engineering the requirements. And we started off with the discussion that what is a role of a method when we talk about requirements engineering, and we differentiated that when we pick a different method to engineer requirements, the system models that we generate, they are different. And although a requirement engineering process is the same, it will involve all those sub processes. It will have elicitation, it will have elaboration, it will have negotiation, specification, validation. It would have all those things. But the way these processes or the details of these processes would be different, or the emphasis on different processes would be different. So we discussed different models of requirement engineering, and one thing that we concluded in our discussion is that there is no ideal requirements method, and it depends on the choice of of the organization with the which kind of model they feel more comfortable. It depends on the technology with which different companies or different people are working with. For example, if people are working on the projects where they need to develop them in object-oriented environment, then maybe they would choose an object-oriented method. Whereas if they are familiar and they are working in structured languages, then maybe a structured method would suit them, and they would make maybe data flow diagrams. So it depends on, so the choice of a method, it depends on the expertise, it depends on the need of the company, it depends on the need of the client, and it depends on the technology that you are using. And we saw that, as we just said, that the system models generated when we use different methods, they are different. And we also discussed that, for example, when we look at that object-oriented method, then there are lots of system models which can be generated. For example, we can have object diagrams, we can have class diagrams, we can have, within object-oriented method, we have scenario-based models in which we can make use case diagrams. And when we make these different models, our models get more enriched. We can put more detail into a model, we can annotate them more, and with time we get more information about the system, so we can have more detailed models. Mainly we discussed three kinds of models. We discussed data flow models, we discussed object-oriented approach, and finally we started on our discussion with the formal methods. So data flow model is based on the notion that system can be modeled as a set of interacting functions. So we saw that we saw the example of a library management system, and we saw how we decompose that system into set of interacting functions which will interact and take some input and transform that input into a certain output that the external entity or the stakeholder desires. Then we also looked at same example decomposed using the object-oriented approach, and we identified different classes, we identified attributes and operations of different classes, we also identified how these classes are going to interact with each other to make a functional system. Finally, we looked at that, and we know that there are lots of problems with these methods of requirement engineering. For example, we know that all these methods that we discussed before the formal methods, they are semi-formal or they are informal. The reason is because the requirements or the system models which are generated by using these methods, either they are natural language based, or they would be some diagrams, or they would be in the form of tables. And so that actually entails that there would be some ambiguity in them, there would be some incorrectness in them, and they may not be complete, or we cannot be sure that they are complete, correct, or unambiguous. So what do we have then? So formal methods give us an opportunity or a representation in which we can model or we can specify these requirements in a mathematical format. And when we say mathematical format, what does it mean? It means that the requirements that we are going to write formally, they would be, we can actually automatically check them whether they are unambiguous, whether they are complete, they are correct or not. So depending on your need, you would use formal methods. But we also saw there are lots of problems with using formal methods, and we discussed that the lack of acceptance of formal methods is a result that because people do not understand it. And we know that the software requirement specification document that is produced, it is written once, but it is used multiple times, and there are different kinds of users who come from different backgrounds. And normally it is very hard to find people who can specify requirements formally, and it would be very difficult for normal users to interpret them. So that is one of the biggest hurdles. So we do not use formal methods that often, and we do not use it for day-to-day software. So when we want to specify requirements formally, we need to be very careful for what kind of system we are going to do that. So normally the critical systems that we discussed, from those critical systems, we pick those critical features and we identify those features, and we only try to define those things formally. So even for the whole system, we do not want to write the formal requirement because they are very expensive. So we discussed these formal methods. We again looked at the example of that library management system, and interesting thing is that we discussed the same example and we engineered requirements, or we decomposed that problem using these three methods. We used a structured approach, we used object-oriented approach, and finally we used the formal methods. And we ended up with different system representations. So that is very interesting that, and as we said, it actually tells us that different methods can be used to generate system models of the same problem. And it depends on your choice of implementation, as I just said. It depends on the technology that you are working with. It depends on your client at times. So there are lots of factors which help you decide which method you are going to choose. But specifically with the formal methods, for normal systems such as the library management system, you will not want to write requirements formally. But just for the sake of understanding and just for the sake of explaining the point that by using different formal methods, you end up with different system models, we use the same example. So let's quickly look at that example and see what did we get at the end when we use different methods for requirement engineering. So as I said, we decomposed the library management system using the structured method. And within this structured method, we discussed data flow diagrams. And we know what data flow diagrams are. We said that they model the flow of data through the system. And we already defined that data flow diagram models the system as a set of interacting functions. So whenever we start modeling the system under this system approach, what we have initially is a level 0 DFD, or we call it a context DFD. And a level 0 DFD is nothing but we say that this learning management system is my overall process, and I have a library user who is going to send some inputs to this system. There are two kinds of inputs. For example, the library user will give the user ID or library card and request for a certain book, and then there would be an output from this learning management system to the library user. Similarly, we also have library staff who will also give some input to this learning management system, which input can be in the form of book details or something. So, and then we said, so this is the level 0 DFD where we model the whole system as one process. But we want to know more about the system, and that is how we decompose DFD. So we make a level 1 DFD. And within the level 1 DFD, we said we have this external entity, which is our library user. And the input, which was user ID, it is sent to a process which would check user details. So in order to check user details, this process needs to communicate to a data store, and this data store would have user details in it, and it will verify whether the user was valid or not. And the other input, which is of the book, is sent to another process which will check the book, whether the book is available or it is already issued to someone else. And then we have this library staff who also punch-ins whenever there is a new book or update records. So whenever you have to check the book, you will go and you will basically, you will have maybe another data store where you will have all the books and their records. So we'll go and check it here, and if the book is available, then, and the user is a valid user, if the user is valid and the book is available, then book is issued, and when the book is issued, there is a notification to this external user, and the account of the borrower is updated. Now we can see that in this particular diagram, what we have is we have certain data that is input to my system, which is library management system, and then there are certain outputs from the system. And I want to know that how this data is transformed into the output. And that is done through these transformation functions or these processes. And this is what data flow diagrams is about, and this is what structured approach or structured method for requirement engineering is about, that we get a system model which is a set of interacting functions. And the same example, when we decomposed it by using the object-oriented method, we first of all started to identify that what are the objects or what are the classes in this particular example. So we came up with lots of different classes. We said that there is a general class of a library user. There is a class of a library user. Then we have a class of library items. And then we discussed different concepts which are related to object-oriented or which are related to class modeling, such as, for example, we discussed inheritance. And we said that for each, there are different kinds of library user. But each library user would have a name. He would have a library ID or something. And he would maybe have an address. Okay. But there are three kinds of library users. We can have student as a library user, we can have a staff as a library user, or we can have other people as the library user. Okay. In case of the student, we need to maintain some extra information. For example, the degree in which the student is registered. We want to know that, whereas we don't want to know this information for the staff. We also want to know the student's admission number. Whereas for the staff, we want to know the staff ID. And for the other people who are accessing the library, we want to know the employer details and maybe the employer ID. So these are the things that we want to know. And we said that using the object-oriented concept of inheritance, what would happen is that all these classes, all these three classes, they are the child classes of this superclass library user. So they are inheriting not only the attributes of this library user class, they would also inherit if library user has any associations with any other classes. And there was another class that we identified, which was the account class. And we said that there was an aggregation association here with the library user, because an account is always associated with a user. If the user does not exist, then there is not an account. So we said that the student, staff, and these three kind of library users, they are not only inheriting these three attributes of library user, they are also inheriting this association with the account class. So student has an association with the account class, staff has an association with the account class, and the others, they also have an association with the account class. Similarly, we started understanding, okay, what are the library items, or what can be the library items? So we said each library item would have an ID and would have a classification. And we said that there can be two kind of things in the library. There can be published material, and then there can be recorded material. And for the published material, we will have a year of publication. And within this published material, we will have more classes. We can have books, and we can have journal articles. So when we started modeling this library management system using this object-oriented method, we started identifying different classes, we started identifying different objects, we started identifying different attributes of these classes. And the next thing was to know that how these classes are going to talk to each other. When do some message would be need to pass between these different classes? So we said that whenever so first thing it was to identify that what are the operations which are related to a certain class, because we know that these classes are going to communicate with each other using these operations, because the message passing between these different objects of these different classes is done through these operations. And we said that whenever a library user, so one of the operations which is associated to a library user is issue a book. So for example, whenever this library user is going to issue a book, he is going to need to communicate to this library item. Okay, and based on this, so whenever the borrow request would come to this library item, first of all, the ID of the book or whatever library item the user wants to borrow, this ID needs to be checked whether this is available with the library or not, and if it's available, then the account of the library user would also be updated using this association. And that is how we started understanding the system. We said, okay, we started off with identifying the objects or the classes. Then we said, okay, what are the attributes of these different classes? And then we started identifying different operations of these classes. And then we started to describe how these classes are related to each other. What is the relationship between a library user and a library item, library user and an account, and library staff and library items. Whenever a new book comes into the library, library staff is going to talk to this class of library item. So there would be a message that would be passed from the library staff to library item, because he is going to update the book records. He is going to add them, he is going to delete them, he is going to dispose them. He is going to do multiple things. So again, you can see that using different methods for requirement engineering, our system model is totally different. The way we started thinking about the problem is totally different. And that is the beauty of it, that you can model the same system by using different methods and you will get different representations. And then finally, we modeled the same system, library management system, using the formal methods. And within the formal methods, we used a model-based specification language, which is the Z language. So we use Z language to model this library management system. And within this Z language, we said that everything within the system is modeled as schemas. So what is a schema, first of all? So we said that a schema has two things. Schema is normally represented in this language in this format, where you write the schema name here, and then you have two sections here. In this section you put your declarations, and in this section you have your predicates. So these are the three main sections of the schema. You have declaration, you have predicates, and you have the name. But when you start modeling a system, there are two things in a system. There is this state of the system, and you have your data invariants, and you have some operations. We are going to discuss them in more detail in our lecture today, but let's quickly look at that example of library management system, and then we'll try to identify later on that how we came up with this state, how we identified these data variants, and how we identified these operations. Now, when we started defining the state of our system, each of these state and the operations, both these things, they are written in the form of schemas when you are using this Z language. Okay. So first thing that we wrote was that the state of our system, which is library, so we named our main schema as library, and this defines the state of my system. So I said that within this library I will have a variable stock, and this stock is a set. So this symbol actually tells that this is a set, and set of what? It is a set of books. And then I said that I will have an other set which is on loan, and each book that is issued is associated to a borrower. So these two sets, they define they are the declarations, but they do not define the complete state of my system. And then I said that all the on loan books, domain of on loan books, are a subset of this set stock. So only the books within my stock I can give those on loan. So if we look at this, now this schema, it defines the state of this library management system. One thing that you would notice here is that I have sort of limited my definition of this library management system. The reason is that whenever you are using these formal methods, you always adopt the minimalistic approach. So you try to model the minimal features which completely define your system. So when we were modeling the system, we said, okay, that there are two things in my library. There is stock of books or stock of the material. So let's assume that there is a stock of the books. So we said, okay, we'll have one set which is stock of set of books. But then we have another set which models a relationship between a book that is issued and to whom it is issued. So, and this actually models a very interesting condition as well. It says that whenever a book is issued, there has to be a borrower against it. So it cannot happen that a book is issued and you do not have a borrower against it. And then there is a data invariant that at no time during the system execution it can happen that the set of on-loan books, it has a book which is not in the stock. So this is a data invariant of the system. We are going to discuss those in more detail, but this schema, it defines the state of my library management system. Now what are the operations that can be executed in a library? We know that somebody can borrow a book. We know that if there is a new book, then library stock needs to be updated. And similarly, if we want to dispose a book, then maybe a book needs to be removed from the library. So there can also be a return operation, that a book is returned to the library. So there can be different operations. So each operation, as we said, it is also defined as a schema. So for example, we start defining this operation that a new book is coming in. So that is my schema name now. And first of all, I would need to decide, okay, whether this operation is going to change the state of my system. And what is the state? State is the variables which define my system. So in our case, we have two sets, a set of stock of books, and then there is another set which models the books to the borrower, which is on-loan books. So I'm going to say, okay, whenever a new book comes in, it is going to change my state, because the variables where my data is held, they are going to change, because whenever a new book comes in, my stock would be updated. On-loan set would not be updated, but my stock set is going to be updated. And then, first of all, I define that whether it is going to change the state or not. This symbol identifies this delta symbol that the state is going to change. And then we say, what is the input? What are the input to this operation? As we normally, whenever we define functions or operations, we identify inputs and outputs. So there is an input to this particular operation, which is this book. And we said when we were defining, when we started discussing this schema definition in Z language, that the syntax for whenever we have a variable, we say identifier comes here, and then the type comes here. So the type here is book of this input variable, and this is the identifier which is used. And this question mark shows that this is an input. So here is the declaration portion of this operation, and now we are going to write the predicates. Okay, so we know that a new book has come in, and we know that when we apply this operation new, the state of my system is going to change, which I have defined here. Now there are two sets. One set is the stock. So I know this stock set is going to change. So I say, okay, this stock prime represents the change in my stock set. And what will be the change? I will increase my stock. So I would have a union operation between my stock set and this new input book. So this book will be added to my stock of books. Whereas my other set, which is on loan, there will not be any change in it. And it is always a good idea, whenever we are applying these operations, that we explicitly write that if there is no change in a certain set, then we write on loan prime is equal to on loan, which says that there would be no change in that particular set. So this is how we define operations, and this is how we define the state of a system. Now, if we look at this particular example of library management system using formal methods, then we have generated a completely different representation of the system. And you can see that this is a minimalistic approach, but to some extent, it defines everything that a library might have. So at this point, we conclude our discussion on those that different methods generate different representation of the system, and the choice of your method depends on the technology that you're using. At times, it depends on the client choice, and it depends on the type of system you're modeling. Obviously, for a library management system, as I earlier said, we will never write specifications formally, because it is very time consuming, and it is not required for this kind of a system, because this is not a critical system. Okay, even if we have slight ambiguities or problems, we can fix them. But just for the sake of understanding, we model the same system using different formal methods, and we get different system models. So in our lecture today, we are going to continue our discussion using these formal methods, and the different concepts that we started or we introduced in our previous lecture, we are going to talk about them in slightly more detail, and we are going to look at another example of modeling a certain system using formal methods. So the first question is, which we slightly answered in our previous lecture, is why we need formal methods. So current methods of software development involves only combination of diagrams, text, and tables, and we actually saw that when we were discussing these different models, then these were the possible representations that we were getting from all those informal or semi-formal models. So no methods are used to test the correctness of the end result in each of the stages of software development. For example, requirement specification, design, and etc. So when we are using these formal methods for software engineering in general, we should be able to test the correctness at each stage. When we are gathering requirements, so whatever requirements we specify formally, we should be able to check the correctness at that stage. When we are designing system formally, we should be able to check the correctness of design formally. So, and what is the problem? Because we cannot establish the correctness, so this leads to contradictions, ambiguities, incompleteness, and vagueness. And as I said, that this is not a good option, or this is not an acceptable option for safety critical or mission or generally critical system. This is not a good option, where failure is not a choice, or whenever you have a failure, you pay a very huge price. So as I said, your choice of formal methods normally would lie with the critical system whenever you're modeling a critical system, and even for those critical systems, when you're modeling those critical features, you want to specify those features formally, because you do not want any ambiguity or any incorrectness in those specifications. So formal methods, they are mathematical. They are an attempt to deal with contradictions, ambiguities, vagueness, incomplete statements, and mixed levels of abstractions. And they are most valuable for systems which have safety concerns, for example, airplane systems or medical devices, or security concerns. Generally, when we define these formal specification methods, they have four things in them. Number one is that they do have obviously formal specifications. Then there are formal proofs, and then we can check the model. And then there is this thing about abstraction of when we are modeling or when we are writing specifications formally, there is a concept of abstraction, or generally there is concept of abstraction associated with formal methods. So we are going to see what are these formal proofs and what is model checking, and then we are going to look in a more detailed fashion particular example of these formal methods again. So first of all, what are these formal specifications? Because our concern here is using these formal methods for requirement engineering. So what are these formal specifications? The translation of non-mathematical descriptions, and we know what are the non-mathematical descriptions. We have diagrams, we have tables, and we have natural language into a formal specification language. It represents a concise description of high-level behavior and properties of a system. So this word is very important, high-level behavior. So we are not going to go into a lot of detail into low-level behavior, but we are talking about the high-level behavior of the system. Well-defined language semantics, support formal deduction about the specification. And we discussed that in previous lecture as well, that what are the different types of formal specifications. We have model-oriented methods and we have property-oriented methods. In the model-oriented method, we construct a model of the system behavior using mathematical objects like sets and sequences. So, first of all, we generate a model. And if you guys remember from our last example that we discussed today as well, the library management system that we modeled, when we were modeling the state of the system, when we were writing the library schema which defined the state of the library, first of all, we tried to model the system's behavior. Okay, so that is how we do it. And when we were writing those operations were changing, were applying different things on those models. And there are different examples. We can use state charts. There is this Z language which we discussed, and we are going to discuss that again today. And then the other category or the other type of formal specification is property oriented, where we use a set of necessary properties to describe the system behavior, such as axioms and rules, and within that we can have algebraic semantics or temporal logic models. But our focus would be on these model oriented approaches, and specifically we are going to discuss this Z language. So what are these proofs? We saw what are these formal specifications. We know that they are a formal or mathematical representation of the requirements or the specifications that we have in the form of diagrams, text, and natural language. So what are these formal proofs? So proof is an essential part of specification. Proofs are constructed as a series of small steps, each of which is justified using a small set of rules. Proofs can be done manually, but usually constructed with some automated assistance. So normally, when we are writing these requirements formally, we can check them. And as I gave you the example that with this Z language, there are different tools which supports writing specification in Z language, and you can run proofs on them and you can check the validity of your model. And there are different tools. There is a tool which is with the name Z-Avis. You can use this particular tool to write formal specifications in Z language, and you can verify it, you can check your model using that. So model checking says a technique which relies on building a finite model of a system and checking that a desired property hold in the model. So there are two general approaches. There is temporal model checking and automation model checking. And you can also use model checkers. For example, SMV is one example. So as I said that whenever we are specifying or whenever we are using these formal methods, there are always formal proofs associated with formal methods, and you check the validity of your model. And specifically when we are talking about writing specifications, then formal specifications are also part of it. And finally, we'll talk about abstraction. And generally, we say that the level of abstraction is high when we are writing specifications formally. So representation of the program using a smaller model. So we only pick the things which matter, and we generate a model using them. As we said that using the model-oriented approaches, first of all they generate a model of the system which defines the behavior of the system. So we are going to pick only those smaller things which actually matter. And what it does, maintaining this high level of abstraction or only focusing at the things which matter, it allows you to focus on the most important central properties and characteristics of the system. And getting the right level of abstraction is very important when we are specifying these requirements formally. So these formal methods, they can be used to mathematically prove the correctness of a system. It helps reduce faults, and formal methods can provide program specifications, define the program, what the program is supposed to do, program verification, prove program does what the specification says it will do. So the verification that we have discussed, it is also going to validate that whatever we are going to make using these specifications, it is going to work. Before we start defining different things which are associated to model-oriented approaches and specifically Z language, these are the 10 commandments of formal methods. Number one is, whenever you are using these formal methods, you need to choose the appropriate notation. So you need to pick the orientation or notation which suits you. You need to formalize, but do not over formalize, because we have already discussed that this is an expensive thing to do. Writing specifications formally is very expensive. We need to estimate costs, that how much it is going to actually cost us when we start specifying these requirements formally, and have a formal methods guru on call, or you need an expert there, because as I said, it's not very easy to specify these requirements formally, and specifically when you need to pick that what are those smaller things, what is the right level of abstraction for modeling this system or specifying the requirements formally for this particular system. That is very critical, and you need somebody who is actually an expert in that, who can actually guide you through that process. And do not abandon traditional development methods. So this is very important, that when you are focusing on this formal specifications, so do not abandon your original methods of requirement specification. You need to document sufficiently. Don't compromise quality standards. So this is again very important. Do not be dogmatic, and test and reuse as well. So if you have already written some formal specification for an earlier version of this product or for a legacy system, maybe it's a good idea to fall back to them and see what you are going to change in this new system. So these are the general things that you need to keep in your mind when you are talking about specifying requirements formally using a formal method. So now we are going to define some of the things which are useful when we are modeling a system. Remember, we are talking about model-oriented approaches. So there are two things in a system. Number one, we have a state, and then we have data invariants. And we discussed those in a previous lecture as well. We discussed state, but we did not clearly define what a state is. So a state is the stored data that a system accesses and alters. So this definition actually helps us understand that library management system example more clearly, that a state is the stored data that a system accesses and alters. So if you remember, when we were defining the state of our library management system, then in the main schema, which was library, we defined the state of the system using two main variables. So we said stock, and we said a set of on-loan books. And we said stock is a set of books, and on-loan is a set which maps the books to borrower. So these two variables, they represent the data which is going to be stored in my system, and by applying different operations, I am going to either access the stock, I'm going to either access the set of on-loan books, or I'm going to change these two sets. So this is the definition of a state. That a state is the stored data that the system accesses and alters. The next thing is very interesting and slightly more difficult and tricky. That what is a data invariant? So a data invariant is a condition that is true throughout the execution of the system that contains a collection of data. For example, maximum number of elements in any system, duplication not allowed in the system, and these kind of. So in our case, in our library management system, we had one data invariant where we said that this domain of on-loan books is a subset of this set stock. Now that is a condition which needs to be true throughout the execution of a system. And it does not matter what operations we apply, this condition needs to stay true. Now a very interesting scenario comes up. For example, if you guys remember, we talked about an operation which was adding a new book to the stock. Now let's assume that you do not update your stock, and the book is lying there, and a library user goes and issues that book. Now if this data invariant is not mentioned, let's assume this data invariant is not mentioned, then what would happen is that your stock is that original stock without that new book, but in your on-loan book you have a book which you have issued to a borrower, which is linked to a borrower, but that is not in the stock. And this is something wrong. It means that, so these data invariants, they help you identify those conditions which will question the correctly functioning of your system. So here, by saying that no book can be on loan unless it is in the stock. So normally, I think you might have actually experienced that at times you go to a library and you see a new book lying there and you're tempted to actually borrow it. But when you ask that whether I can issue that book, the librarian would tell you, no, we still have to update our stock and only then it can be issued. Because there's a serious problem here, because if you issue that book and it's not in the stock, then there would be no reflection of that book. And even if you don't return it, librarian would not know of it. So the stock needs to update it first and only then the book can be issued. So that's why this condition or this data invariant, it's important that it says that the domain of on loan books. So when we say domain of on loan books, so it will return all these books. So it will return set of all the books. We say that this set of all the books, so domain of on loan books is going to return a set of books, should be a subset of this stock, which is again a bigger set of books. So this was the data invariant in that particular example. So again, a data invariant is a condition that is true throughout the execution of the system. So that is important to remember, that when we say throughout the execution of the system, so whenever we apply an operation, whatever we are doing with the system, whether we are updating the state of the system or not, this data invariant should stay true. And then finally, there is concept of operations. So the first thing is that we model our system, and then we want to know, okay, how the behavior of my system is going to behave depending on different things that the user are going to do with the system. So for that, we need operations. So operation is defined as an action that takes place in a system and reads or writes data to a state. So we know now that we have a state and we have conditions, which and conditions are some things which needs to stay true. Does not matter what operations we are applying on it. And then finally we have operations, and operations do two things. Either they change the state of the system, or they just read the state of the system. So there are two things. And when we are writing operations, there are two types of conditions. There are preconditions and then there are postconditions. So preconditions defines whether the operation is valid or not. So first of all, you need to know that whether a certain operation can be applied or not. So in our example yesterday, we did not discuss that an operation has preconditions and postconditions. Whereas whenever we are defining these schemas, so because in our example it was not valid, but we're going to look at that why this precondition is useful and why we actually need to do it, and what are the postconditions. So preconditions, they define whether the operation is valid or not. For example, let's say we are trying to remove a book from our stock. But if this book is not in the stock, so that operation is not valid. So to check the validity of that operation, we need to have a condition that certain book that we want to remove is a subset of this set stock. So that would be the precondition. So for example, we have this schema where we are going to remove or dispose a book, and we know that here we are going to change the state of our system, and we have this book as an input which we are trying to remove. So the precondition would say that I need to ensure that book is a subset of stock. If this condition is true, only then I can update my stock set to reflect that this book is being deleted from the stock set. And what are these postconditions? These postconditions, they define what happens when an operation has completed its action. So let's look at this example of a block handler, and we'll try to understand these concepts of state, how we identify state, how we identify and define those data invariants, and how do we figure out, okay, what operations can be applied on this particular problem. Because remember, we are discussing that model-oriented approach, and within that model-oriented approach, first of all, we need to model the system. Okay? And when we are modeling the system, we identify the state and we identify the data invariants, and we also try to figure out what kind of operations can be applied on this state. So let's look at this example of a block handler. It is a common part of any operating system. As we said that, what are formal specifications? We have natural language, we have diagrams, we have tables. We use that to write or we give it a mathematical representation, okay, which ensures that whatever we are writing, that is correct, it is not vague, it is not ambiguous, and it is complete. So a common part of any operating system, that is a block handler. It provides free blocks of memory to new created files and regain blocks when the file is removed. So very simple, whenever you create a new file, some blocks are associated to that file, and when that file is deleted or removed, it regains those blocks back because that memory space is free. So it keeps track of free blocks or the unused blocks and the used blocks. Whenever a block is freed, it is added to the queue of unused blocks, and similarly when a block is needed, first block from the queue of unused block is given for use. So now we know that if we look at this description, then remember that the first thing that we identify when we are writing that, when we are trying to model the system, is we need to identify the state. And if we remember the definition of state, a state is the stored data in the system which we access or which we alter. So we want to identify, okay, what data. So we can see, okay, that we have set of used blocks and then we have set of unused blocks. So we have two kinds of blocks. So that is what we can get from this particular description. So let's try to understand this problem. What is this problem? So we are saying here that this is our block handler, and these are my set of unused blocks or free blocks. So it says that 1, 3, 4, 6, 9 block, they are free, and these are my sets of used blocks. So whenever a file is removed, what happens is that these blocks, they are added to this queue, and from this queue the blocks are then added to this set of unused blocks. So what happens is that this block 2 is being added to this queue now, and the reason is that because this certain file has been removed, and the next set of blocks are 5, 8 and 11, and this shows that another file is deleted which was a bigger file and it had 3 blocks. So they are also, the file is removed and these blocks are also waiting to be written to the unused set of blocks, and similarly we can see 7. So out of these 2, 5, 8 and 11, they are all freed now and they want to be added to set of unused blocks. Now here is something interesting, that we can see that the set of unused blocks and the set of used blocks, there is nothing common in them. So it cannot happen that a block is in both sets. It is in set of used blocks and it is also in the set of unused blocks. So that is one kind of a data invariant or a condition that we identify, that throughout the execution of the system it cannot happen that a block is in both my used set of blocks and unused set of blocks. So that we know now, that we have identified one data invariant. And similarly we also, from this diagram or this representation of the system, we know that unless a block is removed from the queue, it will be in the set of used blocks. Why? Because the union of this set and this set, it should be all set of blocks in the system. So for example, what could have happened, that we remove 2 from here and we add it to the queue, but it is still in the queue, and let's say if we write 5, 7, 8, 10, 11 and 12, and we have the same set of unused blocks and this is the set of used blocks, although the file to which this block 2 was allocated, this is deleted, but this block is still in the queue. The reason why we are not removing it from this set of used blocks is that because it is not yet added to this set of unused blocks. So another condition is that unless and until a freed block is added to set of unused blocks, it will not be removed from the set of used blocks. Because what would happen that if we do that, if we remove 2 before it is added to this set of unused blocks, the combination or union of these two sets, set of unused and used blocks, it does not show all blocks. So we have a block missing. So that is a problem here. So for example, if we do that, then we have 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we do not have 2. So what would be the union of these two then? The union of these two becomes now 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So where is 2? So where is 2 if we do that? So that is why another condition or another data invariant that we identify here is that we cannot remove a block from the set of used blocks unless and until it is added to the set of unused blocks. So let's try to identify that or figure out that how we identify the states. What are the data invariants? Remember, these data invariants, they are conditions on the data. Okay. And what are the operations for this particular problem? Operations are relatively easier to identify because we know that in our particular example of a block handler, there are 2 possible operations. We can actually get them from this description that whenever a block is freed, it is added to the queue. So adding to the queue is one operation. And similarly, when a block is needed, first block from the queue of unused blocks. So we remove a block and we add a block. So these are identifying operations is relatively simpler, but when we are defining state, then when we are defining these data invariants, they are slightly tricky. So that is where we need to pay more attention on. So what are the state, or what is the data that we need to store in this particular problem? So we identified that there is this collection of used blocks. So one thing that we need to maintain in our system is that what are the blocks which are currently in use, then the collection of free blocks, the blocks which are freed but they are not yet entered into the unused blocks, and then finally we have a queue of returned blocks. So these are the 3 sets. We have free blocks, we have used blocks, and we have a queue of returned blocks. So this represents the data that would be stored in my system, and this represents the data which my system needs to access or which my system will alter when it's in execution. And what are the data invariants now? No block will be marked both as used and unused. So this is a very important condition. So it cannot, we know that we have 2 sets. One is a set of used blocks and the other is a set of unused blocks. So we know that there should not be anything common. So the intersection of these 2 sets should be null. We know that. So this is the first data invariant. The second one is all the sets of blocks held in the queue will be the subsets of collection of currently used blocks. So remember, we have this queue. So the queue should be a subset of this particular set. No elements of queue will contain the same block numbers. So it cannot happen that within your queue you have repetition of blocks, because this is not possible. So the collection of used blocks and the blocks that are unused will be the total collection of blocks that make up files. So as we said, that union of used and unused blocks should be all the blocks in the system. The collection of unused blocks will have no duplicate block numbers, and similarly the collection of used blocks will have no duplication block numbers. So we do not have duplication in the queue, we do not have duplication in the set of used blocks, we do not have duplication in the set of unused blocks. The combined set of blocks in the used and unused should make the all the blocks in the system, and similarly a block cannot be marked both as used and unused. And the final one, as we said, that the number or the blocks in the queue which are waiting to be returned to the unused blocks should be a subset of which set? Set of used blocks. So these are the conditions which should stay true throughout the execution. Remember that this is an example of block handler where blocks are released and blocks are allocated to the files. So this is happening very frequently. Now we need to ensure that it does not happen at any state that these conditions are not true. So these conditions should stay true. Now how do we write these formally? How we define them formally? so that we can actually check the way we have written them, whether they are correct, whether they are complete, and whether they are unambiguous. And we know that, as I said, identifying operations is very easy. We know that we are adding the blocks and we are removing the blocks. So these are the two operations. So this is the code using, or this is the schema which defines the state of the system. Now, as I already defined that, in this schema we have two main sections. We have this section where we have these declarations, and in this section we have the predicates. So this is the model of my system. So I have my declarations here where I am defining those states, and this portion is defining my data invariants whenever I am writing the schema which represents the state of my block handler. So this schema is representing the state of my block handler. So I know that there are two sets which I have in my system. One is set of used blocks and the other is set of free blocks. And then I have a block Q, which is again a sequence. This sequence actually defines that this would be a queue, and it's like a set. It has all those properties of a set, and what does it have? It has the blocks. So this definition says that we have identifier on the left side of this column, and on the right side we have the type. So here used and free are identified, which says that these are two sets of blocks, and this symbol defines that this is a set, and we have another queue. So these are the three types of data that we are storing in my system, which we will access and which we are going to change. So the next portion is tricky, where we said that we need to define all those data invariants, and remember we had quite a few data invariants in this particular example. So few are very easy to identify. The first one said that there should not be any common blocks in this set and these two sets. So we know that the intersection of used and free sets of blocks should be null. And this particular sign says and. So there is no or here. We want all these conditions to be true throughout the execution of the system. So that's why we have an and here. So we are saying and the union of used and free sets of blocks should be all blocks. So when we combine these two sets, it should be all the blocks in the system. So which is true, or which should be true. And then we need to check that for all the sets or for all the blocks. So this sign says for all, and this is an identifier where we'll store whatever we access from this block queue. So we are saying that one by one we are going to check from the block queue. We'll pick each block, and then we'll check that this block I, which we have picked from the queue, is a subset of used blocks. So anything or any block that is here, it should be a subset of this particular set. So we have already checked that. So if we look at these data invariants, then we have defined this, and we have defined this particular. So if we number them, then this was the first data invariant, this was the second data invariant, and let's say this was 3, 4, 5, and 6. Now if we come back here, then the first one, which says used interaction free is equal to null, this is this first data invariant, or number 1, which I've had on this slide. So this defines the first data invariant from my data invariant slide. And this one, which says that the union of these two sets should be all blocks, this is number 4 data invariant. So this is the fourth one that I have written, and then the second one, all the sets of blocks held in the queue will be subsets of the collection of currently used blocks. So this particular one is defining the second data invariant, and then remember we said that there were three data invariants. We were saying that there should not be any repetition. There should not be any repetition in this queue. So it cannot happen that we have another 2 here. It cannot happen. Similarly, there cannot be 1, 3, 4, 6, 9 and again 1. So there cannot be any repetition. So this data invariant, it is defining the third data invariant which I have on this data invariant slide, which says that no elements of Q will contain the same block numbers. So what we are saying that for all I and j which are from this set or the sequence of block Q, because we say domain block Q, and I where I is not equal to j. So we pick 2 blocks from this set or from this queue of blocks, and we say that the intersection of these 2. So when we are saying domain block Q, because each element of this Q can be a set, so we are saying that I is a set and j is a set. We are saying that intersection of these 2 sets, it should always be null. So it cannot happen that there is a 2 here and we have a 2 here as well, or we have a 2 here as well. So it cannot happen. So this data invariant ensures that all the elements of the Q, they do not have any repetition, or they do not have anything common, or no block is repeated in the Q. And what about the data invariant 5 and 6? Where are they? Where we said that there should not be 2 blocks with the same numbers in these 2 sets. Where are they? So we cannot see actually them here. So by definition, this set, it actually defines that there is no repetition. So this is something which is defined, which is part of this definition of a set. And by definition, when we say that used and free, there are 2 sets of blocks, we are actually ensuring that there is no repetition in them. So by definition, the invariants 5 and 6, they are handled here. So this particular schema block handler, it defines the states and it defines all the data invariants that we mentioned in our previous slides. So next we look at the 2 operations that we defined. The first one was removing the block and the second one was adding the block. So when we remove the block from this queue, what we are going to do is that we are going to update 2 things. Because when the block is removed, for example, we remove 2 from here, then our queue needs to be updated. The head of our queue will point to this, so it will be our new head. Similarly, this 2 would be deleted from this set as well, and it will be added to this set. So this would happen when I apply my remove operation. So the first thing I know when I start writing my remove schema is that this is going to change the state of my system. And there are no inputs, because I automatically know what I need to do is that I will remove the head of the queue and add it to the set of unused blocks. Okay, so that is what I'm going to do. So first I define the precondition. So this is the precondition for this particular operation. And remember we said each operation can have a precondition and they can have a post condition as well. So what is the precondition? That number of elements in the block queue, they are greater than 0, they are not 0. So we can only remove something from the queue if there is something in the queue. So we know that this precondition stays true, so we go ahead with the operation. So what are we doing now? We are saying that we are going to change the state. We know that here because we said delta block handler. We are going to change our data that is stored in used set, we are going to change the data which are stored in the free set, and we are going to change our block queue. So we say used prime would be now equal to used, and this sign says that whatever is in the head of our block queue, which is in this case is this particular element 2. Remove that from this set used. So this particular statement is saying that whatever is in the head of the queue, which is 2, remove that from this use set. So my new use set after this particular line would be 5, 7, 8, 10, 11 and 12. So this would be my new set. But I am also changing my free set as well. So what I am saying here, that my free set would be a union of whatever is in the head. So my free set now would become 1, 2, 3, 4, 6 and 9, because my block 2 is removed from this used set of blocks. And because my tail was pointing, earlier my tail was pointing here and the head was pointing here. So now I am saying that block Q, new block Q is equal to tail of block Q. So now my head is, or my Q will look something like that, and this would be my head of the Q and this would be tail of the Q. So this is how it will be updated. So these are the things which would happen. Similarly, if we look at this add block operation, then what we are doing here is that again we are saying that we are going to change the state of the system. So we have a delta block handler, and in this particular operation we had an input as well, which is a block or set of blocks. So first thing we are checking is, or the precondition here is, that whatever blocks we want to add to this queue, they should be a subset of this used set of blocks. So that is what we are checking here. And we know that whenever we are adding, so we remember by the definition or the textual description of this block handler, we said that whenever a file is deleted, then those blocks are added to the queue. Okay. So we did not say that the blocks are straight away added to the free set of blocks. We said that the blocks are added to the queue. So there is not going to be any change in the set of used blocks, because we are just adding them to the queue. And remember, unless and until these blocks are added to the set of free blocks, we do not delete them from the set of used blocks. So there is no change in the state of these two sets. So the new used is equal to used and the new free is equal to free. So we're mentioning that, and we are saying, but there is a change in the queue. So what we are saying that a new block queue, a new element is added. So for example, let's say if this was my queue and another file is deleted which was stored in blocks. So what might happen, for example, let's say this was my queue 5, 8, 11 and 7. So what I'm saying here is now that if, let's say, another file had these two sets of blocks 10 and 12. So what I'm saying that this is now added to my queue. So another file is deleted and these blocks are added to the queue. So this is what is happening here. So we have seen in this particular example that what are the different things that we need to mention when we are defining requirements formally using these model-oriented approaches. For example, Z language is what we discussed. We specifically discussed the syntax of this Z specification language. First of all, we knew that everything that we write in these Z languages is in form of schemas. And we said that the schema, we define the state of the system, and when we are writing the state of the system, we identify what data needs to be stored in the system, and by data we mean whatever things we need to access and whatever we need to alter, that is the data, and that defines the state. And then there are some conditions. Our system, whatever is the state of the system, those conditions should be true, and those are called data invariants. So for this particular example, or using this particular example, we sort of tried to figure out that how we identify those data invariants. And then finally we figured out that how we identify these operations. So that is all that we are going to discuss about formal methods. And just one concluding remark, that having looked at these two examples, the example of library management system and example of this block handler, we can sort of relate that modeling a system formally is not an easy task. And you need an expert to sit with you to identify the states, to identify the data invariants, because they are the tricky bits. So that is why we say that when we are modeling the system formally, remember those 10 commandments, that you always need to pick those smaller things which matter, so the level of abstraction is high. You only model the smaller things which are actually important and which are actually critical. And you need an expert who is with you. But the advantages of modeling in such a fashion, they are pretty obvious. That when we model a system formally, then we can actually check whether what we have written it is correct or not. So formal methods, they are very effective and they are very efficient, they are very useful when we want to ensure that there are no ambiguities in the requirements that I have written. But there is always a cost associated with it. And as I mentioned in this lecture and in the previous lecture, that you choose to write requirements formally only for critical systems because of the cost that is associated with it. So that is it from our discussion on methods of requirement engineering. In our next lecture, which is going to be the final lecture of this course, we are going to look back at the course, what we have learned, where we started off, and what were the important things that we have discussed throughout the course. So till then, take care and Allah Hafiz. Assalamu alaikum.